evening, everyone. We are in the week 11 problem solving session of the NPTEL course, Control and Tuning Methods in Switch Mode Power Converters. And week 11 is about large signal controller tuning methods. I am Teja Golla, a fifth year research scholar working under Dr. Santanu Kamat at Embedded Power Management Lab, IIT Kharagpur. Let me share my screen. Let me know once you can see my screen.
Yes, sir, it is visible.
Okay. So in the last week, I have not taken any session because that was conducted in the last week. So previously we have discussed about trajectories because we needed that for large signal tuning. So we have learned about how to draw the trajectory, how to get the eigenvalue, stability, etc. And then we have also discussed about the large signal tuning derivations for low transient, how we can design controller considering the trajectory into mind, and then how we can shape the trajectory so that we can get the near time optimal or time optimal recovery and what are the requirements, etc. So in this week also, sir has mainly covered about those aspects like how the controller can be used to improve the response, improve the transient response of the system, and why it is important. And I'll not be going into the details of the derivation, but we'll solve more problems so that we can uh, understand the large signal tuning and how to design the controller using the large signal tuning so that we can get the optimal transient response. So we'll be solving more problems today, and then along with the problems, I'll also teach few concepts whenever it is necessary. So we'll start with the PID controller because for voltage mode control, we'll be using PID controller. For current mode control, we'll be using PI controller. But PI controller, there is no issue as such. But PID controller, we have seen that there is practical uh, issues in terms of implementation because of the derivative. So can you tell me why we cannot implement the ideal PID controller and why we have to go for practical PID controller?
Ideal PID controller has improper transfer function, so it is not physically realizable.
Yes, very good. So let me just quickly note it down. So we have ideal as well as practical. So if we take the ideal PID controller, if we write the transfer function say GC of this, we will have KP plus K by S plus KD into S. So now the KDS part is the improper part, improper transfer function, and cannot be practically implemented. So now we will go for practical PID controller. So in practical PID controller, we know that we'll add a small term in the denominator of the derivative, tau ds, where tau d is much smaller than 1. It means that we have placed a very high frequency pole only for the practical implementation. So now this can be practically implemented because now it is a proper transfer function, whereas this is improper transfer function. So if you write this is improper, proper transfer function. So now we have to see that this is practically implementable because it is proper transfer function. So this is something that we have already discussed. I have just quickly summarized. Now, the first question that I wanted to ask today is what are the effects of PID gains on the overshoot as well as settling time and steady state error. So now let me make a table quickly. So we have PID gains over here. Uh, so what did I ask in the question? Three things, which are overshoot, settling time, and steady state error. So we have overshoot, settling time, and steady state error. So now we will see individually, if we increase the gains, say we have KP, if we increase KP, what happens? If we increase KI, what happens? If we increase KD, what happens? So can anyone tell me if I want to see if I am increasing KP, what will happen to the overshoot? It will increase or decrease?
Overshoot will increase.
Overshoot will increase. So we should actually remember this, but we should try to understand why it is happening. What happens if there is a low transient, say? So when there is a low transient, the output voltage will see a dip, right? So whenever there is some error, then KP will try to multiply by that error, right? So there will be KP into V error. So there will be an increment in the control voltage. So now if the KP is more, then the increment in the control voltage is more. So the control voltage will increase very quickly, rapidly. So now the inductor current has to rise quickly. So there will be very large overshoot, and then eventually it will come to the new steady state. So with this, the overshoot will increase. And what about the settling time?
It has a minimum impact on
Yes,
settling
very
time.
good. So it KP doesn't actually have any impact on the settling time. So it will only be impacting overshoot as well as steady state error. So it has minimal impact. What happens to the steady state error if KP
It will
increases?
decrease.
It will decrease.
Decreases.
It will decrease, but one thing you should keep in mind that it will never become zero unless there is integrator. So only with the proportional control, error will never become zero. It will only decrease. So ideally, we can think that if I make KP infinite, then steady state error will be zero. But now if we see if the KP is infinite, overshoot will be very high and the op amps will get saturated. So we cannot also go beyond certain value of KP because that also will not be practically implementable because say error voltage is 100 millivolt or say error voltage is 10 millivolt. So now if the KP is 100, then control voltage is 1 volt, right? If the error is 500, then it will be 5 volt. But op amp voltage can be plus or minus 5 volt. So now control voltage cannot go beyond 5 volts. So now no matter how much you increase KP, the voltage will get saturated at 5 volt. So that will not be reflected in the response because the op amp is saturated. So that's why practically we cannot go higher and higher gains. Also because of some dynamics and the limitations of the controller and the overall implementation, the system might go unstable if we keep on increasing KP. So this we have also checked in the previous like last week lecture where if we increase the gain, we have seen that the trajectory can be rejective and then it can go unstable. So there will be a upper limit of the gain beyond which the system can go unstable. So that is also something we have to keep in mind. So KP, higher KP, higher KP can cause instability. Also, it might saturate the organ. So is this part clear to everyone? What we are trying to do here? KB part is clear? Hello.
Yes, sir.
So now coming to K, what happens to overshoot?
Overshoot will increase.
Overshoot will increase again. The same thing happen. Overshoot will increase and settling time
Increases.
increases. And then error
It will become 0.
0. So we will have 0 error. So even if you increase or decrease Ki, eventually it will become 0 error because of the integrator. 1 by S term will have 0 error. But by settling time will be increased because Ki has that that integrator, right? So Ki has that integration, so it has memory. So if Ki is more, then there will be huge overshoot. So it has moved away from the steady state. Now, in order to come back, it will take time because of the, like, you can consider like an inertia of the integrator. So if K is small, then it will reach the steady state faster and then settling time will be less. But if K is more, then it will slowly, the system will become more sluggish. The system will take time to change its integrator value. So more is the Ki, then it will take more time to come to the settling time. Also, if we increase Ki, then there can be oscillations in the system and then it can also cause instability because it will never uh, reach that steady state. It can, like if you see the control voltage, it will never reach one certain control voltage. Either it will be above or below. So higher Ki can cause oscillations in the system. And higher Ki is not at all acceptable. So we should be very careful with the Ki as well as Kd. So now tell me what happens if we increase Kd. Understood. Steady.
Go to overshoot and settling time will decrease.
Yes. And steady state error.
And minimum impact.
Minimum impact. Very good. So basically, you can consider derivative as damping. So it will damp out the system. So whatever overshoot that is being caused by the proportional as well as the integrator, that now will be reduced by the derivative, and then settling time also will reduce because it has more damping. So KD can be used to dampen out the system, but if you have higher KD, then it will actually causes issue because it will amplify the noise, right? So if there is any noise, say V naught is at 1 volt, and then because of noise, it has become 1 millivolt extra, or say 1 millivolt extra. So 1 millivolt is very small. We can consider some noise is there 1 mil. So now if I consider KD to be 1, then it will contribute to 1 millivolt in the control voltage. But say if my KD is 10, then it will be amplified to 10 millivolt. So now the control voltage will change and then some duty ratio will change and then system will respond to the dynamics. Say if my KD is 100, then it will become 100 millivolt. 1 millivolt noise can become 100 millivolt and then now system will respond to that new control voltage. So KD can amplify the noise, which is also not good. So high KD is not at all good, even though it will reduce the settling time. There is an like the upper limit because of the noise amplification, because that is not at all good for the system stability. Any slight change or any noise that will be amplified and then the system will respond to it. So that is not what we want as a, like, if we are targeting a robust design. Higher KD can amplify the noise. So now, say we have designed a controller, and now if we see that the system is overdamped, and now we want it to like make it relatively lesser damped, then we can play with KDs, which is actually controlling the damping of the system. Say if you want to speeden up the system, then we can increase KP so that the overshoot will be increased. So there will be quick reaction to the transient. At the same time, we have to play with KD so that the overshoot will not be too much so that it will damage the system. So we can actually play with the gains and see how the system is responding. But how do I know how much KP should I take? How much K should I take? How much KD should we take? Because KP can vary from 0 to hundreds. K can also vary from any value to any value. Same with the KD. So there are infinite possible values of KP, KD, but there can be only a limited range within which my system will react in a way that will satisfy the load requirements or the application requirements. So for that, we need to have a proper design methodology. So that's why we have learned all these things, because now I know that increasing KP will increase overshoot, so I can do trial and error method, right? But how long will I do the trial and error method when there are infinite possibilities? So we need to have some set of guidelines, so I can get some KP KD values. Now I can play around that KP KD. Say I have gotten KP 10, K to be 10,000 and KD to be 5. So and then system is more or less meeting the requirements. So now if I want to speed it up, now I'll slightly increase KP and see whether it is meeting my requirements. But in order to go to that values of KP, KD, we need to have proper guidance. So for that we have learned how to design the controller, and for designing the controller, model is necessary. So that's why we have learned modeling. Then we have learned about the controller design, both using small signal and large signal. But say we have gotten the KPK KD gains. Now if we implement in the actual plant, and then we have seen that the response is not as per the simulation, because there can be unmodeled dynamics, and there can be some noise, or there can be some other issue that that are there in the hardware, like open saturation, which we have not considered. Then we can fine tune the gains around the gains that we have obtained using the design, and then we can make sure that the system is performing in the way that we need. So now we can use this knowledge to fine tune the KPK KD. But first, what we have to do is we have to model the controller, sorry, model the system, and then design the controller. And then we can simulate it and check whether it is proper or not. If not, then we can fine tune the gains by just changing the gains around the values that we have obtained. And then say now it is meeting, then you can implement in the hardware. And see whether it is actually meeting the target specifications or not. Say if it is not meeting the target specifications, then again you have to simulate with the slightly different gains. Say I have checked that for my KPKKD, my simulation is working fine, but in the hardware, there are oscillations in the system. It means that maybe Ka is more. So we have to go back and then reduce the Ka and see whether we are still meeting the requirements or not. And then we have to implement in the hardware, because what will Ka do? The main uh, the objective or the like the function of K is to maintain zero steady state error. So we need not need very high Ka. K's job is to achieve zero steady state error, and KP and KD can be used to improve the transient response, as also mentioned by sir in the last week. During the transient, KP and KD respond. During steady state, K will be responding, because once the steady state error is zero, output of proportional output of derivative will be zero. Only K will have some value because of the integrator, because of the memory. So accordingly, we have to fine tune the gains so that the hardware will work in the way we want. So this is all about the PID controller, practical PID controller, and how it affects the overshoot settling time and steady state error. And I hope I was able to give you insight so that you can uh, like remember, no, not remember, understand how these are affecting the overshoot settling time, steady state error. So you need not remember. So you can, whenever you're also simulating, you can see that say the steady state error is not zero, then you know that Ki is not there. If you want to improve the settling time, then you have to increase KD or decrease Ki. So now you know what or how you can play with the gains to change the response of the system. Is this part clear? Or if you have any doubts, you can ask. Any doubts until this point? So we have Arun, Parvati, and Riddhi.
No, sir, it is clear.
Oh, So now we
Sir.
can, yes, yes. Yes,
No,
Anand.
sir, no doubt.
Okay. So if you have no queries, then we can move to the second question. So in the second question, let me read it out for you. Consider an ideal buck converter with the following specifications. And then it says V in is 12 volt, V naught is 1 volt, inductance is 150 nanohenry, and capacitance is 1.2 millifarad. What is the characteristic impedance? So can anyone tell me what is the characteristic impedance?
Square root of L by C.
Square root of L by C. Yes, very good. So for the given condition, what will be square root of L by C? Can anyone calculate?
Point 011.
Okay. Others also please give it a try. Then we can cross check our answers. So I have given a buck converter and I am asking what is the characteristic impedance. So characteristic impedance is defined as square root of L by C. So I have given L and C. So please calculate, and then you should also be very confident with the calculations because in this course calculations are like key in almost every problem except few conceptual questions. So you should be very careful with the calculations. So you'll feel more confidence as you solve more problems. So I want you to be fast, quick enough. Also not to make any mistakes in the calculations. So in the exam, few questions can be lengthy, but there will be calculations as you know, as you have solved all the assignments. So has anyone calculated? Okay, once you calculate, please let me know. Then I'll also start calculating, and then we can cross check our answers. Or if you have already solved, you can put it in the chat box so we can cross check later.
Why not 1 1?
0.001.
0.011.
0.011. Okay. Let me calculate. So ZC is square root of L is 150 nanohenry. 150 into 10 to the power minus 3 by 1.2 milli is 12 into, sorry, nano is 10 to the
Sir,
power
nano.
sorry,
Sir, L is nano.
Nano, and then 12 into 10 to the power minus 4. So now I can cancel this 4 times and 350 times. So it will become 12.5, right? So square root of 12.5 into 10 to the power minus 5. So if I bring this, it will be square root of 125 into 10 to the power minus 6. So 125 is 25 into 5, right? So 5 root 5 into 10 to the power minus 3. So let me calculate this. We have 5 root 5 into 10 to the power minus 3. So it is 0.0111. Yes. So you have calculated it correctly. So the characteristic impedance ZC is 0.011. So I hope everyone is able to get the same answer and you are clear about this problem. So this problem is clear, right? How to calculate the characteristic impedance.
Yes, sir.
So now let us move to another problem. So this problem is a little bit lengthy and it involves calculations, more calculations. But I have given like first part and second part are the same, but only load step change is different. Let me read it out for you. Consider an ideal buck converter with the following specifications. Gain is 12 volt, V naught is 1 volt, inductance is 150 nanohenry, capacitance is 1.2 millifarad. For a load step-up change of 10 amperes, what should be the proportional gain for optimal recovery? And what will be the value of peak current? And what will be the voltage undershoot? Same thing we have to calculate again for a load step change of 30 amperes. So I have given for two set of values so that we can practice it better. So for this question, we'll be needing certain like expressions that we need to remember. As a student, you need to remember certain expressions so that it will be helpful for you in the final exam, and it will also save your time. But I'll just note down the three expressions here so that you can also take a note of this, and then it will be beneficial for your assignment as well as the exam. So KP, can anyone remember what is KP value? Okay, if not, I'll just quickly write. So we have KP is equals to C by pi delta I naught to square root of platform. So one thing I wanted to share with you is when I was also doing coursework and like I was also learning during my BTech bachelor's. So there was like there are many courses where we need to remember a lot of formula. So one of the students have asked sir that sir, like what is the purpose of remembering this formula if we are not going to like use it in the like practical life, right? So you may also ask like why do I need to remember all the formula if I can go back and then refer to that formula and then calculate the gain. So like as a part of learning, we first are learning why it is needed or like what is the purpose of it. And then we have learned how to derive the expression, how to derive this gains and how the gains can be useful to achieve optimal trajectory. So first we will be learning the concept around it, but also we have to remember some formula, although they may not be like we may not be remembering this formula throughout our life, but as far as this course is concerned, sometimes we might have to remember the formula. We might forget after the course, like I myself may not be remembering this formula, but during the learning process, it will be kind of a training for our mind so that we can also remember certain things which will improve our memory power. Nowadays, we are not memorizing anything because everything is available online and everything is saved to Google. But we you can consider this as a practice of putting a test to your memory power so that you can remember as much as possible, as many expressions as possible for this course. But we are humans, we'll forget things with time if we don't use it on a daily basis. But once we forget, then you can always come back to this course and then get the formula and then do. But yeah, so this was the like answer that our professor has given to us. So I'm also like passing the information to you, because this is what you might be thinking, like why do I need to remember all the formula, because after the course I may not be using. But it's not like that. For the like for certain courses you need to remember certain formula so that it will save time. In the exam we are testing whether you are aware that you need to use this formula uh, in this question, whether you have understood the concept or not. But every time you will not get time. Also, it's not a good practice to derive all the expressions during the exam. So you have to remember certain things like formula, and that's how you know learning is. So it's part of the learning. But I'm giving the formula here, so these things you need to remember for your final exam. So lambda is dependent on step up as well as step down. So lambda has two values, one during step up, one during step down. So lambda is square root of 2 into V in V ref, and then 2 into square root of V in minus V ref into V. So we have this V. So this is for step up, and this is for step down. So this is the optimal proportional gain that you will be getting for buck converter during load step up transient as well as during load step down transient. So maybe I'll keep it on the side. This is for the gains. Now we also have peak current as well as voltage undershoot. So sir has given the expressions for those as well. I'm just noting it down. So we'll have I peak I naught one plus delta I naught. Delta I naught is the step. I naught is the steady state current before the transient. So which I have not given. So you can consider I naught one to be 1 ampere. So before transient, it is at 1 ampere load step. Now on top of that, a 10 ampere load step and 30 ampere load step is applied. So the new steady state current is 11 amperes and 31 amperes. So I naught one plus I naught plus. So this is the steady state, new steady state current, but there will be a peaking on top of the steady state current. So that term is delta I naught by 2V in square root of 4V in V minus delta I naught square Z square. So this is for the peak. Now the undershoot V1 undershoot is V reference, which is the steady state voltage minus whatever it is dipping. So we'll have delta I naught square ZC square by 2 into V. So this is something that you should take a note. Okay. So now for the same set of gains, I mean same set of specifications, we already have calculated ZC, which is 0.0111. So I will give ZC value. So we know that ZC is 0.0321. So we have this already. Okay, so now we'll do the first part. First part, what is it saying? Load step up change of 10 amperes. What should be the proportional gain and what is the value of peak current as well as what will be the voltage undershoot. So please note down the specifications. So once you note down the specifications, I'll display the expressions for this KP as well as peak current and voltage undershoot. So please note down input voltage is 12 volt, V naught is 1 volt, inductance is 150 nanohenry, capacitance is 1.2 millifarad, and then current steady state current is 1 ampere, and load step changer 10 ampere and 30 ampere. Once you note it down, please let me know. Then I'll scroll down and display the expressions. Have you noted down the specifications of the converter? Can I scroll down?
Yes, sir.
Okay. So these are the expressions. So first I want you to, so this is step up transient. So lambda is 2 into square root of v in v reference. I have given the values for all of them. Kindly calculate expressions of IP as well as V1 as well as KP. Once you calculate for part 1, which is delta I naught is 10 amperes, then I'll calculate and we can cross it. Then we'll move to the second part, which is for 30 amperes. Or maybe you can first calculate KP, all of you calculate KP, and then let me know. Then I'll calculate, and then we'll move to IP, and then we'll move to V1. So has anyone calculated KP for part 1? So part 1 is delta I naught. So first we are solving A part, which says delta I naught is 10 amperes. So for this case, what will be the KP, optimal proportional gain? So if anyone has calculated, please mention in the chat box, then I'll start solving. Also, please take a note that there is less than a minute, and after that the meeting will end. Then we will join back, and then we'll continue the problem solving session. So if this meeting ends, kindly join back. Arun, Parvati, and Riddhi are able to solve for KB for the first part. What value are you getting?
5.54 into 10 raised to 3.
Okay, 5.54 into 10 to the power 3. Okay, let me calculate. Also, if this meeting ends, kindly join back. So KB is C into lambda, which is square root of 2 into V in V reference. C I have given 1.2 millifarad. 1.2 10 to the power minus 3 into 2 into square root of 12 into 1 by L into delta I naught. L is 150 nanohenry. And then I naught is 10 amperes. So let me calculate and let us see how much value we are getting. So I'm getting 5.5 into 10 to the power 3 as you have mentioned. Yeah, so as I was saying, sometimes we may get very high gains that it may not be practically implementable. So we need to check in the simulation and we have to see and do thorough testings, and then we have to see But with this high gain, whether we can actually implement the optimal control, that may be also a question. And also we have to see what is the maximum current, peak current that it will reach during the transient. If it is exceeding the limits or the protection limits, then we have to put a saturation. Then we may not be able to achieve optimal transient response. So all these things we need to keep in mind. But whatever we are calculating, we are just calculating theoretically, keeping that it is possible to implement. But practically, there can be many other issues which we need to consider and do a lot of testing before we finally implement in the hardware. So, have you calculated I peak?
3.85 ampere.
3.85. Okay. 3.85, or it should be more, right? Because this itself is 11. I naught 1 is 1 ampere and delta I naught is 10 ampere. So this itself is 11. So it has to be more than the steady state values. So please cross check and let me know. Parvati, you also calculate and let me know what value you are getting.
Uh, 13.8, sir. That plus delta I zero I missed.
Okay, 13.8. Parvati, are you also able to solve? I'll just give some more time. In the meantime,
Yes, sir.
Arun, you are getting
13.85.
okay.
13.85.
Okay. So I'll just solve for I peak. In the meantime, you can calculate V1. So I peak is I naught plus delta I naught. So Riddhi, you can also solve so that we can see whether we are getting the same answer. So I peak is 1 plus 10. And then delta I naught is 10 by 2 into V in. So it is 2 into 12. And then square root of 4 V in V ref. So 4 into V in is 12. V reference is 1 minus delta I naught square into ZC square. ZC square is 0.0111. Delta I naught is 100. So 10 into delta I naught square is 100 into 0.0111 square. This is the expression that we'll be getting. Let me just solve it. 1 plus 10 plus 10 by 24 into square root of 48 minus 100 into 0.011 square. So we're getting 13.88 amperes. Very good. So I peak is matching. So I peak is 13.88 amperes. So if we are using these gains and assuming that it is practically implementable for 10 ampere load transient, we are getting a peak current of 13.88 amperes. So it is more or less close to 10 amperes. So it should not create any issue or damage any switches or inductors, but we have to go through the data sheet and then check whether it is practically possible, whether it can sustain this current or not. Else we have to choose for higher rated components. So now you can calculate V1, which is to calculate the undershoot. how much dip we will be seeing in the voltage. Once you calculate, let me know what value you are getting, then I can start solving.
So 0.999 I got.
0.999, 999, right?
Yes, sir.
Okay. What about Arun and Riddhi? Are you also getting the same?
Same, sir. 0.999.
Okay. So basically, it means that there is no undershoot. So whatever last minute tuning we are doing, we just totally remove the undershoot. If we are able to implement this, then this will be a very good design because we are practically like completely eliminating the undershoot. So now the third one. We have V1 is equals to V reference minus delta I naught square into ZC square by 2V. So delta I naught square is 100 into 0.111 square by 2 into V, which is 12. Okay. So now let me calculate 1 minus 100 into 0.011 square by 24, which is 0.99948. So we can say that V1 is 0.99948. So the undershoot will be 1 minus this, which is actually very less than a millivolt, so half a millivolt. Practically, this much less undershoot may not be possible because it is in the range of noise. Theoretically, this is what we are getting. Practically, it will be, of course, more than this. So that thing you should keep in mind. So there is theory that says something, and then there is practical that says something else, because there are many things that we will not be considering in the theory, like noise, and then there are unmodeled dynamics, and then there are switches which are non-ideal. We consider ideal switches, and then inductance will have some parasitic that we have not considered in the uh, derivation of these gains. We have considered the ideal converter, ideal switches without any parasitic, ideal inductance without any parasitic, ideal capacitance without any ESR, and then we have considered constant current load. So we have considered ideal situations, and we have considered assumption that there are no parasitic. Whereas in the system, first of all, there are parasitics, and switches are not, ideal. Switches have some delay. So there is a delay in the system. We have not considered op-amp delay. We have not considered op-amp saturation in that. So there are all these practical things which are not considered in the theory. So that will come in the practical implementation. So we need to keep that in mind, that whatever values that we are getting in theory may not exactly match in the hardware. So is this part clear?
Yes, sir. Sir, one doubt.
Yes.
In the previous week also we studied something like time optimal control. There
Yes,
we
yes.
used another formula for I peak current delta I0 into root of D. So how can we distinguish which one to use? Because here also we are using the same terminology, optimal recovery.
Yes, actually both are same. So we'll get the same, the I peak value. So sir has used a different approach in deriving these expressions this week, but both are, if you calculate, both will remain the same there and here, because there sir has considered an approximation. So if you see this delta I naught square ZC square, this is very small value. So if you neglect this, then this will become 2 into square root of V in V reference, and then okay, let me just okay, now that you have pointed out, let me just solve this. Okay, so what sir has considered in the previous week is, sir has considered this very small, because ZC is very small, so this sir has considered 0. So now if we solve for this expression, then we'll have delta I naught by 2 into V into, so square root of 4V in V ref is square root of 2, sorry, 2 into V in into V reference. right? So now we have delta I naught by 2 will get cancelled, square root of V in, and here we will get square root of V reference. So now this will become delta I naught into square root of D. So that is the assumption that sir has considered in the previous week. Now we are dealing with the actual total expression without considering any assumptions. But even if you neglect this term and then calculate, it will come very close to this. So it will not make any difference drastically that it will affect the response or change the value drastically. So that's why sir has made that assumption to get an expression that will be simpler. But in the exam, with and without this, if you calculate whatever answer that you will be getting, both the values will be within the range that we'll consider it as a right answer. Say this is coming 13.88. If we neglect this and make it 0, it will be slightly higher. So in the exam, we'll consider the range say 13.5 to 14.5 or 15. So we even when you neglect and so basically with and without approximation, whatever answer you'll be getting, both will be within the range that is considered as a correct answer.
Okay, sir, clear.
So if you don't have any doubts, now we'll move to the second part, which is 30 amperes. So we have calculated for 10 amperes and we will update these values. Now we'll see if the load transient is more, how it is affecting our gains, KP, how it is affecting our peak current, how the undershoot. So theory says Kp should be reduced because it is inversely proportional to delta I naught. Let us see. And undershoot also should increase, which means V1 should go down because delta I naught is increasing. Zc is same. So let us see how much it actually changes the value. So we can also get an understanding of how delta I naught is affecting Kp as well as Ip as well as undershoot. So now we have V part. We have delta I naught is 30 amperes. So I'll just show the formula and you have already noted down the values. So quickly calculate the gains and then we can cross. So this week is also simple if you understand what to use at, because basically it's all about large signal tuning. So once we get the gains, the questions will be basically about the gains. How what is this value? What is that value? So you need to remember the formula. Then you should be able to solve the problems and should be able to score good in the assignment. Similar type of problems you can expect in the final exam, where they can ask what is the gain, what is the undershoot, etc., etc. You have to see whether it is a buck converter or boost converter. So accordingly, you have to choose the formula and calculate what the gains.
For KP 1.83.
1.83. Okay. Or should it be a little bit more? 1.83 into 10 to the power 3 or just 1.83?
Yes, sir. 1.83 into 10 to the power of 3.
Okay. So let me just wait for others. Once they also solve it, then I'll calculate.
One 1.84 into 10 raised to 3.
Okay. So let me then solve for it. So we have Kp is C into lambda, which is 2 into square root of V in P reference by L into delta I naught. So we have Kp equal to C, which is 1.2 milli into lambda, which is 2 into square root of V in into V reference by L into delta I naught. L is 150 nanohenry into I naught 30 amperes. So let me check how much I'm getting. 1.2 into 10 to the power minus 3 into 2 into root 1 by 1 into 10 to the power minus 9 into 30. So I'm getting 1.8 into 10 to the power 3. Is this what you are getting, or did I make any mistake?
Sir, 1.83.
84. Okay, yeah. So I'm getting 1.847 into 10 to the power 3. So I got 1847.52. So now if you see, this is lesser gain compared to what we have obtained previously, because delta I naught has increased. So now here we got 5,000 something, here we got 1,800 something. Again, we have to check whether it is practically implementable or not. Then we will not get time optimal response, but we'll get suboptimal or near time optimal response. So we have calculated KP. Now I want you to calculate I peak and then V1 as well. So all of you please try. And then once you solve, then I'll solve, so we can cross the answers.
Sir, I peak 38.7.
38.7, okay. Let us see what Arun will get, then I will solve. Rishi, I hope you are also solving. If
Sir,
you
I
are
got
also
39.65.
39.6, okay. Okay, then I'll check. Riddhi, I hope you are also solving. Please, solve along with us so that it will benefit you in the assembly final example. So we have I naught plus delta I naught. One thing I'll do, I'll just copy paste in the next page so that I need not scroll up and down. I'll keep it aside. So my IB is I naught, which is 1 plus 30 amperes plus delta I naught by 2 into V is 24 into square root of 4 into V in VRF, which is 4 into 12, 48 minus delta I naught square is 30 square into 0.0111 square. Okay, so we'll have 31 plus 30 by 24 into square root of 48 minus 900 into 0.0111 square. So I'm getting 39.65. Parvati, please check. I think you might have made some mistake. So I think is coming 39.65 amperes. Parvati, please check your calculation, then we'll go further if you also getting the same IP.
Yes, sir, I got 39.65.
Okay. So please solve for V1 and then we can also cross check our answers.
Sir, V1 I got 0.995.
0.995. Okay. So it is like 5 millivolt undershoot. Let us wait for Arun, then we start solving.
Yes, sir, 0.9954.
So let me just solve for V1. V reference minus delta naught square ZC square 2 into V. It is 0.995. Yeah. So we are getting around 5 millivolt. So as you see, it is comparatively more because of the large tangent, and also the math says the same. So if we are increasing the load step transient, then our KP has gone down because it is inversely proportional to delta I naught, as well as peak current will of course increase because the load step itself is more. So now like this term will increase because it is proportional to delta I naught. Previously, it was just 3 amperes above the new steady state. 2 amperes basically. Now it is almost 7 to 8 amperes extra. We have to check whether the inductor and the switches will support this current or not, and then only we can design. Say if the inductor cannot support this much current, say switch cannot support this much current, and switch supports only 35 ampere, 36 amperes, then we have to put a saturation on the current and forcefully turn off the switch whenever the inductor current hits that peak. So that is, more of the protection and practical implementation aspects. And with this, we are getting this much voltage undershoot is now 5 millivolt. But as I said, practically it will be more because of many other parasitic as well as dynamics and model dynamics that we have not considered in the derivation. So is this question clear? Maybe I'll just quickly summarize. So in this question, I have given an ideal buck converter with the following specifications, which are 12 volt input, 1 volt output, 150 nanohenry inductance, and capacitance is 1.2 millifarad. And then the steady state current is 1 ampere. And for a load step up transient of 10 amperes as well as 30 amperes, I have asked what will be the proportional gain for optimal recovery and what will be the value of peak current as well as what will be the value of voltage undershoot. So first I have listed down the proportional gain for both load step up as well as step down, and then I peak values, and then V1 from where we have calculated the peak value as well as undershoot for both the load step up cases. So is this question clear?
Yes, sir.
Okay. So in such case, we can move to our next question. So in this question, one mistake is we'll not have a peak current as well as voltage undershoot because it is stepped down. So we'll have only one part. So I'll just modify this. So in this question also, same thing. We'll be considering the same ideal buck converter with the same specifications. Now I will change the I naught step down, right? So now previously it had some current and now it has step down of 5 amperes and step down of 20 amperes. So I will give you initial I naught, say 30 amperes, whether it may or may not be needed. I naught one in the calculation. Say it is initially at 30 amperes. Now there has been a load step down of 5 amperes, and then final current is 25 amperes. And in the part 2, we have load step down of 20 amperes, which means it has stepped down to 10 amperes. So what are the values of Kp? Yeah, so for part 1, 5 amperes, and part B, 20 amperes. So please calculate. Once you calculate, I will also cross-check.
36.765 into 10 raised to 3.
36.76 into 10 to the power 3. Parvati, are you also able to get?
Lambda value, how much it was?
So you have to take step down because I have given step down transient. So you have to take the second one. Are you able to solve? Parvati, are you able to solve?
Yes, sir.
How much are you getting?
So 3.67 into 10 power
3.67 into
power 5.
10 to the power 5. Okay, let me just check. So we have KB. C is 1.2 milli. N is 150 nano. Delta I naught is 5 amperes. Lambda is 2 into square root of V in, which is 12. And V in minus V reference is 12 minus 1, which is 11. So from here, we'll have to come from KP. So yeah, it can be huge, but let us see what can be get minus 3, 5, 15, minus 9 into delta I naught is 5 into 2 into square root of 12 into 11. So it is coming very, very high. So which is 36,765. So 36.765 and 4. So which is again theoretical value. Practically we have to see whether this will create an issue or not. So delta I naught 5 ampere is done. Now let us solve for delta I naught 20 ampere. So I hope everyone is getting the same KP for the first part. Now before we go to second part, I want to mention one additional thing. For step up and step down, the gains need not be the same because the expression for the proportional control is different for both of them. Unless V reference and V minus V reference are same. So which is very specific condition. So for any converter, the step up optimal gain, proportional gain, and the step down low transient optimal proportional gain need not be same, and it can be different. So either we have to detect whether it is load step up and load step down, and then accordingly use the gains. So which is called gain scheduling. Else we have to use conservative gain and check the simulation and see whether the response is according to our requirement or not, and then use the same gain throughout the response. But uh, kindly note that the gains may not be the same for load step up of 10 amperes and load step down of 10 amperes, because uh, the conditions are different, and then the gains will be of course different, and so the expressions are also different. Yeah, so now please calculate for this new set of load transient, and let us see whether we are able to get the same expression or not.
So 9.19 into 10 raised to 3.
9.19 into 10 to the power 3. Okay, let us check. Also, as delta I naught is increased, Kp should decrease. So basically, it should be 1/4 of that, as delta I naught is increased by 4 times. So we can also do by that way. Okay, so you're saying 9 point something into 10 to the power 3. So I hope it is correct. Let us wait for Parvati. And Riddhi, I hope you are also
Yes.
following.
Sir,
Yes.
9.19.
Okay, 9.19 into 10 to the power 3. Let me just calculate. It should be by 4. So I think it's correct. So Kp is 1.2 into 10 to the power minus 3 by 150 into 10 to the power minus 9 into now 30, and then 2 into square root of 12 into 1 minus 1. So now 10 to the power minus 3 by 150 into 10 to the power minus 9. Square root of 12 into 11. So 2 into square root of 12 into 11, right? 1.2 million. So I'm getting 6127. Am I making any mistake? Oh, sorry, this is 20 amperes, right? Not 30. So this is 20 amperes. So my bad. So it is coming 9191, 9.191 into 10 to the power 3. So your answer is correct. Yeah, so this is what we are getting, 9.191 into 10 to the power 3. So let me just quickly summarize this problem, these two problems, because it is critical. So as you know, we have designed the controller using small signal model as well as large signal model. With small signal model, there is model validity issue because of the assumptions that we have considered during the modeling of the converter. So if we want to achieve faster or better performance when there is critical requirement or very ultra fast transient requirements, then we need to design the controller using large signal model, because small signal model is not valid beyond certain band. So for that large signal model, we have used the trajectory based tuning, and then for the trajectory based tuning, we need to understand what is a trajectory, how to draw it, and how to get it, and all the details regarding that, which we have learned in a dedicated week. In that week, we have learned about all these things, and then in the last week, we have learned about the controller design using the large signal tuning and how to get the PID gains or PI gains for large signal tuning in order to get the optimal response. So there will be one switching completely on, followed by completely off, and then it will reach the steady state. So we have seen how to calculate the gains for both step up as well as step down, for load as well as reference transient. And then we have seen that Sir has shown the simulation, how the small signal and large signal based design will significantly change the transient response in terms of settling time as well as voltage undershoot, which are critical for certain applications like data center and EV, automotive, etc. So in that case, we can use large signal theory. But I have given a few, only load transient problems, and we have seen how the load step up transient will vary the proportional gain as well as the peak undershoot as well as peak current as well as voltage undershoot. So here we have considered one buck converter where the input voltage is 12 volt, output voltage is 1 volt and 150 nanohenry inductance as well as 1.2 millifarad capacitance. And in the first part, we have considered it is already at steady state of 1 ampere, and then there is a load step change of 10 amperes, and then uh, how the gains are turning out to be, and we have written down the expressions and we have calculated Kp as well as I peak as well as V1. So these are the values that we have gotten for the first part where delta I naught is 10 amperes. Now if we increase the delta I naught, we can tell by intuition that Kp as this is multiplied by 3, this should be divided by 3. If we calculate this is 5.5 by 3 is around 1.8, which is what we are getting. Similarly, if you see I peak, so delta I naught is more, so this is more, also this is more. So the extra term is also increased with delta I naught. Also, this term will increase because this is corresponding to the new steady state. So this is the new steady state. This is the extra term that we are getting on top of the new steady state. So the new steady state will anyway be higher because of the larger step transient and because of the dependency on delta I naught, the extra term on top of the new steady state will also be more because of increment in the delta I naught. And now V1 will be more, V1 will be less because delta I naught is more. So the undershoot is more when the load transient is more, which is also obvious because the capacitor will discharge more in order to supply the charge to the output, which is higher in this case. So the capacitor will discharge more, and now the controller has to ensure that it will come back to the original reference voltage, which is V reference. So this is about the load step up transient. Now coming back to the load step down transient. So the Kp is dependent upon whether it is step up or step down transient. For step up transient, lambda is 2 into square root of V in V reference, and for step down, it is 2 into square root of V in into V in minus V reference. So accordingly, the Kp will change. So we have calculated for a load step down of 5 amperes, what will be the proportional gain, and for a load step down of 20 amperes, what will be the proportional gain. And this term remains constant if it is a step down transient. So the only dependency of Kp is on delta I naught, which is varying in these two cases. So if the delta I naught is increased, then the Kp will decrease. So we have increased delta I naught by 4 times. So the Kp should decrease by 4 times. So as you can see, Kp by 4 will give you this new Kp. So there is less than a minute. If this meeting ends, kindly join back. But do you have any queries until this point? How to calculate the optimal gains for optimal proportional gains for optimal transient response? Please join back if this meeting ends. Then we'll move to new problems on new topic. So now we'll move to a new topic, which is dynamic voltage scaling. So dynamic voltage scaling, what does it exactly mean? I'll give some brief introduction, then we'll move on to the problem solving. So about processors. Processors are now everywhere. Everything needs processing because everything is digitized. The best example is smartphone. So smartphone has a processor, right? So say this is the processor. So this is our processor that is sitting inside our mobile phone, Android or Apple. So it needs a voltage to operate. Let's say it has to compute something. It has to process certain applications. So it needs power. So it has to draw some current. Also, it has to draw. It needs certain voltage. So this is the load now. Previously, whatever we are considering in our converter, that is our constant current load, resistor load. But here processor is the load. So before this processor, if you see inside a mobile phone, so there will be DC-DC converters sitting next to you. Certain DC-DC converters. So all these are DC-DC converters sitting next to you. So this is one DC-DC converter. This is another DC-DC converter. This is another DC-DC converter. This is another DC-DC converter. So all these are DC-DC converter. So similar to processor, there is RAM, there is memory. So in a PC, we have DDR5 RAM. So all these needs power. So these DC-DC converter will supply the power. So now the processor may not be always fully loaded. Say my mobile phone is in sleep condition, then it will not draw any power because majority of the applications are in the sleep mode, or maybe they are running in the background. But once I turn the mobile and then say I open some application, say any game as such, say PUBG game I have opened. So now it needs to process a lot of things, because now it has to process all the applications of the PUBG game that demand very high current. For graphics, it needs high processing. So the mobile will heat up, right, whenever you are playing games, because it is processing a lot of things. So it needs to process all the CPU, GPU, meeting the requirements of that game. So now that this game is going on, the processor will draw the current, and it also has certain voltage. So now this certain voltage, say it is 1 volt. So the processor that is sitting inside our mobile phone, the voltage can vary from 0.9 volt to 1.8 volt, around this range. Say this is 0.9 volt to around 1.8 volt. So now why this voltage is varying? Because not just processor, but there is also RAM, there is also memory. So each of these loads will be requiring certain voltage levels depending upon how they are designed. But also this voltage can vary on the go. Why? Because say my load, here I'm considering the PUBG game. So my PUBG game was off. So I have not turned on the game. So my load current I naught is at load, very light load condition. So now I have opened the application, any game. So now my game, the application demands current. So this current has to be processed, or the application has to be processed by this processor. So it demands current. So now it demands current. Sorry. So now it demands current, high current. And then as long as I operate it at high performance mode, the mobile phone has to process all these things. And then again, once I turn off, it will come back like this. So now for this V naught, if we draw voltage V naught, so there will be undershoot, and then it will set it, and then there will be voltage overshoot, and then it will set it. So now say my V naught is at 1.8 volt, or say 1.2 volt, for example. So 1.2 volt. So initially, when the game is not turned on, or when I'm not playing the game, the processor was sitting at 1.2 volt with very light load condition, supplying very negligible current for basic applications like screen or something. Now I have opened the game. So now the processing is at its maximum. So now the phone has to process a lot of things as I'm playing game. So the current requirement was huge, but my controller must ensure the voltage should come back to 1.2 volt. So depending upon load step up and step down, there is voltage undershoot as well as voltage overshoot. So now this V naught has come back to 1.2 volt. So now there is some additional, or advanced algorithm which is called as droop control, that sir was mentioning in his lecture, or something called active voltage positioning. So what this will do is, so whenever there is high current, we will change our reference. So what I mean to say is, initially it is sitting at 1.2 volt. But when there is a increment in the current, I need not bring the V naught to 1.2 volt. I can keep it closer to 1.2 volt, but lesser than 1.2 volt. So whenever there is an undershoot, I will not bring it back. I'll make sure, or I'll keep it at a lower value. And once there is an undershoot, I'll bring it back to 1.2. So the processor which needs 1.2 volt, it will not it will not only work at 1.2 volt, right? It will have a certain threshold. So now what I'm trying to do is I'm taking advantage of that threshold and making sure that my output voltage is within that threshold, so that the processor will still perform at that high performance, and then there will be no performance issues when I'm playing game on the application. But what is happening? I am now making sure that V0 settles faster. So now this voltage can be at 1.2 volt. This can be, say, 20 millivolt lesser, 0.02. So now it is coming at around 1.18 volt. So whenever there is high application requirement or high load current requirement, then I'm reducing the voltage of the processor so that I can reach to the new steady state faster. Also, the power consumption is depending upon the voltage as well as current, right? So when the current is high, if I reduce the voltage slightly, while I am not losing anything at the performance of the processor, then I can reduce the power consumption. So in this way, we can change the voltage that like the processor is operating at. Then in that case, we can reduce the power consumption. Also, we can improve the transient response. So this is called active voltage positioning or voltage troop control. So basically, if you draw the graph, so V reference at light load condition, it is V reference, but as the load increases, I am reducing my reference so that it will operate at a reduced voltage, reducing the power losses, increasing the efficiency. Also, my transient response can be improved because I need not bring the voltage all the way back to 1.2 volt. Instead, I can make it settle at a relatively lesser voltage. So is this concept clear? Hello. So if things are not clear, I'll explain again, but please let me know.
Clear, sir, clear.
Oh. So sir has mentioned about the dynamic voltage scaling. So dynamic voltage scaling. So the term itself says that the voltage is being scaled dynamically. So on the go, voltage is changing. It need not be during load transient. Sometimes there can be reference transient as well. So say the load is at the same condition, but voltage now has to change from 1.2 volt to 1.8 volt. So that is called dynamic voltage scaling. So sir has mentioned a few aspects regarding the power loss as well as time delay. So I'm just mentioning them down. So the dynamic power, P dynamic, is proportional to the VDD, that the voltage at which the processor is operating, square, and then proportional to switching frequency. Also, the time delay, T delay, is inversely proportional to VDD. So if my VDD is more, power consumption is more. If my switching frequency is more, my power consumption is more. If I can slightly reduce my operating voltage without losing the performance, then I can save, uh, power, and then I can make the phone work more efficiently. And then also the battery health will be more. So I can use my phone for a longer time because my power consumption is less. Similarly, there is a trade-off, because if I reduce the voltage, then there will be some delay. Like all these digital logics, say CMOS logics, they'll take some time from the input to output, right? So that delay is inversely proportional to VDD. So if the voltage is high, then the delay will be less. If the voltage is low, then the delay will be more. So we need to optimize the performance as well as the battery health as well as the efficiency. So we should not lose the performance. At the same time, we should reduce or optimize the power losses. So that is the overall objective. And then there is a trade-off between this. We cannot operate at very high voltage where the power loss will be more. Also, we cannot operate at very less voltage where the delay will be more and performance will be, compromised. So we should have a middle voltage like in between so that the performance is also optimized as well as the losses are also optimized. So this is the science behind this dynamic voltage scaling. And as this is more related to processors, I have considered, mobile phone as an example. So is this clear?
Yes, sir.
So let us solve one problem quickly. So here I have asked you to consider two processors. One processor is operating with VDD of 1.8 volt, operating at 100 megahertz, and another processor B is operating at VDD equal to 1.2 volt, operating at 200 megahertz. So which processor consumes more power? And then determine the ratio of power consumption, and then which processor exhibits higher time delay, and calculate the ratio of the time delays. So can you tell me which processor will consume more power?
Processor A.
Okay, and how are you saying that processor A consumes more power?
So that V square into F, that product, if we calculate for the two cases, for the first one it is higher.
Okay, yes, very good. So we'll use this formula and then we'll check. So P dynamic is proportional to VDD square into FSW. So, let us solve A and B together, A comma B. So we can calculate power consumption by the processor A is some constant K into VDD square 1.8 square into 100 megahertz, which is 10 to the power 8. Power consumption by B is K, same proportional constant into 1.2 square into 200 megahertz. So it is 2 into 10 to the power 8. So now if I calculate the ratio PA by PB, I will get 1.8 whole square by 1.2 whole square into 2. Now I will see whether it is greater than 1 or less than 1. So I'll get 1.8 square divided by 1.2 square into 2. So it is 9.8, which is 1.125. So you are correct. Processor A is consuming more power. So PA by PB is coming out to be 1.125. And then processor A consumes more power. Okay. So now part B, which processor exhibits higher time delay?
First one.
By so
1 by
It is
VDD.
inversely proportional to frequency.
inversely proportional to voltage. VDD.
Sorry, sir. So it is
Second one, right?
second one.
Yeah. So if we calculate C comma D, then time delay, TDA, TDB. So if we consider time delay of A and then time delay of B, it is inversely proportional. So I'll consider another constant K dash by its voltage 1.8 by K dash by 1.2. So we'll get 1.2 by 1.8, which is 2 by 3, 0.666. So we got time delay A by time delay B is 0.666. So which means processor A exhibits lesser time delay, or I can say higher time delay. So processor B exhibits higher time delay. So processor A is consuming more power, but the time delay is less. As we have discussed, there is a trade-off between the performance as well as the uh, power consumption. So maybe one processor is operating at high power consumption, other processor is performing better. So this is the competition nowadays smartphones has. It's not just about performance, it's also about optimizing the power losses so that the battery health will be also more. So there are many things that come into picture. We are pushing the limits. So nowadays smartphones are having high performance, as well as everyone needs their battery health to be stay longer. So which is like a trade-off. You cannot have both, but that's all research is about. So how I can optimize both? It's not like I'll get the best performance and then best battery health. There is an optimization. That something has to be compromised. So that's how smartphones are doing, pushing the limits on both the sides. One is performance, one is the battery health. So is this problem clear? Problem 6.
Yes, sir.
Yes, sir.
Okay. So now we'll go to problem 7, which is again related to both dynamic voltage scaling, which is load transient as well as reference transient. So if I want optimal performance for load transient, what are the requirements? And if I want optimal performance for reference transient, what are the requirements so that I can achieve better transient performance and for load as well as reference. So how to proceed with this? Any idea, or should I give clue?
Please explain, sir.
So, the question, what question is about is, say, if you want to have a better load transient performance, which means I want minimal undershoot as well as minimal settling time. Similarly, reference transient, I want very less settling time, and then the peak should be smaller. Like that's the best requirement, right? So now uh, what leads to that better performance. So here what I'm trying to say is the requirements are, first of all, the recovery should be optimal. So optimal recovery, and with that optimal recovery I'm trying to reduce the overshoot or undershoot, as well as I'm trying to reduce the settling time, and I'm trying to reduce the peak current, inductor peak current, because I want the peak current to be minimal. I want the settling time to be minimal. I want the undershoot as well as overshoot to be minimal, while also achieving the transient recovery. So sir has given one comparative table. Let me just take a snip out of this. Recovery time, voltage undershoot, and So there is a trade-off again. So everything has trade-off. In life, nothing, is better in everything. We have to make compromises in certain things. Yeah. So if we consider the step reference transient, so this is 2C into delta V reference, V in minus V reference into V reference by LV in. So in our question, all are fixed except inductance and capacitance. So you tell me whether we need high peak current or low peak current.
Low peak current.
Low peak current. So for low peak current, what should be the capacitance and what should be the inductance?
Small capacitance and a large inductance.
Small capacitance and large inductance. Very good. So if I consider step reference triangle, for IP current to be minimal, I am getting so minimal IP, I am getting small capacitance and large inductance. But if I consider too much large inductance, then recovery time will be penalized, right? So small capacitance will lead to less recovery time. Recovery time should be small, or like the settling time or recovery time. But if we consider too much large, then it can penalize the recovery time. So large inductance might penalize recovery time. Then step low transient. Step low transient. So now for low transient, say my recovery time has to be small, whether inductance has to be small or large. First of all, this is independent of L and C, so no issue here. Coming to this recovery time, whether we want small inductance or large inductance.
Small inductance.
Small inductance. And for voltage undershoot, whether we want minimal or maximum.
Small inductance.
Small inductance and capacitance.
Large capacitance.
Large capacitance. So if we are targeting, minimal recovery time as well as overshoot, we are getting small inductance as well as large capacitance. Now, if you see these two things, they're quite the opposite, right? Exactly opposite. So I cannot have small inductance and large capacitance because then I'll suffer for the reference transient. If I have small capacitance and large inductance, then I'll suffer for low transient. So now we have to consider again the trade-off. Similar to like last problem, here also there is a trade-off between low transient and difference transient. So we need to, consider conservative inductance and capacitance and make sure our controller will ensure that both low transient and difference transient are according to the requirement. So we cannot have, best of both worlds. We have to compromise and then have to come in between so that we can have good transient performance and good low transient performance, not best transient performance with best reference transient with poor low transient or vice versa. We need to have both decently good enough, so that's why we have to choose things accordingly. So now tell me, for low transient, what is needed, small inductance or small capacitance? Low transient,
Large capacitance.
large capacitance and small inductance, right? So small inductance and large capacitance. So for low transient, we'll get A and D. So now for reference transient.
The small c and
Small
large L.
capacitance.
Yes, small capacitance and large inductance. So B and C. So they are like 180 degrees phase shifted. They need the exactly opposite requirement. Yeah. So these are all the problems that I wanted to discuss today. Let me just quickly summarize. We have not, rigorously dived into theory because it's more of derivations in this week. So that's why I've skipped that part and tried to solve more problems so that it will be more interactive and also more helpful for you in the assignments and final exam question for you. So today we have discussed about started with the PID gains and how they are going to affect overshoot, settling time, and steady state error. So we have uh, drawn this table and we have seen how they are affecting, and we have understood the math and logic, intuition based logic, how things are getting affected by increasing the KP, KI, KD. And we have also seen what are the consequences if we use higher KP, higher KI, higher KD, and how it is going to affect the response of the system. Then we have discussed about characteristic impedance, which is again simple, straightforward problem. Then we have discussed few important problems where we have discussed about how to calculate the proportional gains for optimal recovery, and for that condition, what will be the value of peak current as well as voltage undershoot for different load step up transients. And here we have considered 10 ampere and 30 ampere. I have considered buck converter. Kelvin tomorrow will be considering boost converter. So I have given an ideal buck converter with some specifications, and for this load transient, how to calculate these values. So I have given the formula here, which you might have to remember for solving assignments as well as final question paper. So now using this formula, we have calculated KP as well as I peak and voltage undershoot, and we have seen how it is dependent on delta I naught. So depending upon delta I naught, these values may increase or decrease depending upon the dependency, whether they are directly proportional or indirectly proportional. So we have considered two set of load transients, and we have seen how things are changing. In the next problem, we have considered load step down transient as proportional gain is different for step up as well as step down transient. We have seen how the proportional gain is changing for different step down load transient for 5 amperes and 20 amperes, because it is inversely proportional to delta I naught. If the step down transient is more, then KP has to come down, which is what exactly we are getting from the math. And also from the intuition, we can say that if delta I naught is increased by 4 times, then KP should be decreased by 4 times, which is again what we are getting. Then we have discussed about dynamic voltage scaling. So I have given one example of a processor in a mobile phone and gaming application, and how the voltage should change depending upon our requirement, and how it can be improved by droop control, where the reference voltage is reduced with I naught, and with that we can reduce the power consumption, as well as we are not compromising anything with the performance. We are making sure that output voltage is tightly regulated, but we are reducing the power consumption so that the battery health can be extended and the efficiency can be optimized. And we have seen that again there is a trade-off between the power consumption as well as the time delay. So performance versus battery health or efficiency. And then we have considered one problem where there are two processors with two voltages and two operating frequencies. And then we have seen which consumes more power, and also which processor exhibits higher time delay, again, like a trade-off between the performance as well as efficiency. In the final problem, we have seen another trade-off, which is for the load transient as well as reference transient. So for getting the ideal or the best optimal recovery for load transient as well as reference transient, which means a reduced undershoot, overshoot, reduced settling time, and reduced peak current. What are the requirements in terms of inductance and capacitance, keeping all the input voltage and reference voltage constant? We have seen that there is a very big trade-off, because per step reference transient, we need small capacitance and large inductance, whereas per step load transient, we need small inductance and large capacitance. And there is a trade-off. So we have to design keeping in mind that we meet the requirements for both reference transient as well as load transient. So this is all about week 11. If you have any queries, you can ask. Else we'll meet again in the next week with the final week, which is week 12. Any queries you have?
No, sir. Thank you.
So if you don't have any queries, then I will end this session here, and I wish you all the best for week 11. Please do well. We are approaching towards the end, and I think sir will also be taking one live session where you can ask any questions that you have, and you can expect similar type of questions in the final exam, like similar to that of assignment. So please consider assignment with utmost importance, and I wish you all the best. See you in the next.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, and yeah, good night.